Hey there! Welcome back to the Fundamentals of Electrical and Computer Engineering. This is Lecture 6, and we should be somewhere around week 8. So, this lecture is going to be very conceptual. We're not going to touch the math for these devices until next week or later, but I thought it was important to break apart the idea of the devices and how they work from the math of the devices, because they're both kind of involved. So, with that said, let's get started. We're looking at devices that store power. These are really common. You're gonna see them a lot. They require some understanding to work with, so let's do that. So far, every device we've had has either been a source, so, the round guys, the diamond guys, or batteries. And remember that you can either have a voltage source or a current source, and these are dependent sources, right? So these either have a voltage that is related to something else, some current or voltage in the circuit, or they produce a current that relates to some voltage or current somewhere else in the circuit. But other than sources, we've had resistors, right? Just these guys. Let's use consistent colors. There we go. These guys. Or sometimes I represent them as these guys, because frankly, this is a generic device. And I was hoping that would kind of prime us to being, okay, there's other devices, and those can also have some impedance, right? So we'll get there. But why have we only dealt with sources and resistors so far? Well, frankly, it is easier to learn the math on resistors. Because resistors they're real numbers, or more, they are described by real numbers, and they are linear, right? They don't require any differentiation, d by dx. They're not a derivative or an integral, right? They're normal, regular numbers. So that makes them kind of nice. Also, in the real world, everything has an impedance. So everything, including the wires, has an impedance. Now, we have made assumptions that get rid of the impedance in a wire, right? And in a source. Those are our ideal assumptions. So in this class, only resistors and other devices have impedance. But in the real world, we have to take into account the length of wire we're running, if it's, significant. Within a little Arduino circuit, it's not really significant. You don't really have to think about it. But like transmission lines, those the high power lines that string up Vegas, those are hella lossy, okay? You have to consider how those wires are also resistors. So, all that to say, it's just easier to work with resistors and get used to them. And we have made some assumptions that make, the nitty-gritty not so stressful right out the gate, right? So, there are other types of devices. But we're going to stick to the following. We're going to stick to something called a capacitor and something called an inductor. At some point, I might put out supplemental lectures that talk about things like diodes or transistors. But that's going to be A, very high level, and B, supplemental if we have the time for it. So, mostly, the important part is capacitors and inductors. Alright, so devices that store power. These are the symbols of capacitors. And this is the symbol of an inductor. So this and this have no set direction, right? Kind of like a resistor has no set direction, so we assume it's positive and negative, and then positive and negative. We make the same assumption for these two symbols. Positive, negative, positive, negative. This is a special resistor. All you need to know is that the flat side is the positive side. So that's kind of like how a battery implies its direction with the long end. This one implies its direction with the flat end. But these are the same device, right? These are both capacitors. So these two both store power, but they do it in different ways. In different ways. So let's go through them. So capacitors store power as charge. Okay, we can kind of vibe with that, right? They are controlled by voltage. So the voltage on the capacitor controls its maximum. So what that means is that a voltage connected to it is the most voltage a capacitor can hold, okay? So capacitors are made out of two major components. There's two metal plates, and then there's something called a dielectric. A dielectric. So this is an insulator. So a non-conductive material, okay? So like plastic, air, water, something that does not conduct heat or electricity like that, or at least is a poor conductor of them. So these two metal plates create a potential difference. A potential difference between the two plates. Because you can have charges here and here, but charges behave differently inside the dielectric. So essentially, it's non-conductive, right? Non-conductive. So charges don't pass through it. They don't pass through. Instead, they get stuck in the dielectric. So this requires a little bit of material understanding. So say we've got some copper here and some just plastic here. Okay? If we were to put some kind of voltage, or if we were to run a current through these, well, so conductors keep those charges, and I'm using negatives because it's an electron, right? So those charges hang out around the outside. They are then easily transferable to something else. If you touch this charged orb of copper, you're gonna get zapped. Because it holds that charge, or conducts it, around the outside. Plastic, on the other hand, is non-conductive, right? If you were to put a current on this, the charges hang out on the inside and they concentrate there. they don't transfer out very easily. So we've sandwiched something that is conductive on either side of something that is non-conductive, and we have loaded a current on it. So this thing's got charge, and it creates a potential difference. So there's a voltage across this because of the high potential in here and the presumably low on one side and the presumably positive voltage on the other side. There's a potential difference here, so it stores energy. A capacitor is not a source. It cannot generate energy. It cannot generate voltage. But it can store it. So how do we describe a capacitor? What value do we care about that tells us about this specific device? So it's described by its capacitance. And you might see the word capacity in there. So yeah. We represent it with C, and we measure it in a unit called farads, after, you guessed it, a dude named Farad. And we represent that unit with capital F. So, capacitance is a material property relating the dimensions of the dielectric. So this section to the ease with which electrons can move through it. So this dielectric is a specific material. And that specific material has some value we call permittivity. Permittivity. So permit, right? This is the this section, right? So this is the ease with which electrons can move through a material. So the equation we get is epsilon, length, width, over depth. Okay? So this dimension, width. This dimension, length. This one is depth. Okay? And honestly, I'm not going to ask you to remember this or to use it, because frankly, understanding the concept of permittivity is kind of rough, because that requires you to think about the atomic level and the way a material is structured and how electrons then move through that somehow. And that's a lot, so we're not going to look at that. But I do want you to understand that this is a calculable value. You'll probably just get it as a value instead of the calculate part, but it's a calculable value, and it relates to the specific characteristic of the material between the two plates. So, in a circuit, capacitors are kind of like a bathtub. So, they need to be filled. And they need to be filled by a voltage source. Well, bathtubs need to be filled too. They have to be filled by a water source, right? And they will drain over time. Bathtubs have a drain, and it takes time for a full bathtub. You know what? I'm not going to use yellow. That somehow seems wrong. Full bathtub to drain down to nothing. right? So do capacitors. It takes time to fill up the capacitor. It takes time to empty or use up all the stored voltage in a capacitor. Then, the other thing is, they start empty. They start empty unless told otherwise. If someone is kind enough to pour you a bath after a long day, so you can just go relax, then you've been told that, hey, the bathtub's full and waiting for you. Well, you're gonna be told that the capacitor has been charging and is full. So, unless there's something that indicates the bathtub is not empty, you can just assume that the bathtub lives empty. Same thing. It also takes time to fill and to empty, right? You know that you have to wait to pour the bath. You have to wait to empty the bathtub. Generally, you don't have to sit over it and wait. Generally, the bathtub will empty on its own once you leave it. But anyway, all of these things we have to take into account when we think about analyzing capacitors in circuits. There's also something else we should think about, which is that the dielectric is non-conductive. So, technically, there's a gap here, right? But we'll get there. We'll get there. Let's just let that simmer. So, without doing any math on this, okay, without math, we're going to look at the following situations. We're going to look at when time equals 0, the switch closes. So that is a loaded statement, right? So this is a switch. This is a switch. It generally looks like some kind of lever. It's got connectors on one side, and this lever can go up and it will disconnect the circuit, and when it's down in place, it connects the circuit. So this is a switch. When it's closed, the wire is connected, circuit's connected, everything's like normal. When it's open, it's not. It's disconnected. That's an open circuit. That is a gap in the line. So at t equals 0, well, if something is changing position, it can't do that instantaneously, right? We know that we have to be looking at different situations. We have to look at different points in time if the same object is going to be changing positions. Kind of like how you can't really move a ball from one place to another without time passing. Even if it's very, very fast, you can't move a ball and measure its change in location without also accepting that some amount of time has passed. So, same difference. So, we're going to say that if we've got this number line of time, that whatever before 0 we're at, the switch is open. And so at t equals 0, the switch will close. T equals 0, switch closes. Let's use a color that's a little more visible against white. Switch closes. From here on out, we're looking at a closed switch. All right? Then we're going to look at t equals n, which is greater than 0. So what I mean is t is somewhere here over here at n. And the switch will open again. And from then on, we're going to look at t equals some time very much greater than n. So we're looking at an order of magnitude or something bigger than n. We're looking at a number line way over this way. And that's still t. And this one is capital T. And the switch will stay open. So this will suddenly disconnect and suddenly not change for the rest of time. So these are three very different states, and we're going to go explain and explore why they are different states for this circuit to be in. So, starting out, t equals 0 when the switch closes. The switch closes. We got a circuit. So, we've got a circuit. So this has a current in it, this has a current in it. We know that because, actually, let's use this node here to explore that, right? So if this is plus minus, plus minus, plus minus, same thing, right? Then we've got a current going this way, current going this way, and a current going this way, right? Because we have a closed circuit. We have a full, fair circuit. So the capacitor in this situation, the capacitor, is connected to the source. Now, so when this closed, this became a valid circuit, and this was connected to that valid circuit through this node. The capacitor is filling, because actually, we don't have a current through this capacitor. We have a current to this plate, and this plate is tied to ground. Because everything on this line is tied to ground, right? So we know that we have 0 volts on this side of the capacitor, and we have voltage on this side of the capacitor. Cool beans. So we do not have a current going through this, right? So since the capacitor is an insulator in the middle, the current cannot pass through it, and it acts like an open circuit. Right? We mentioned this a little bit earlier. So this circuit actually looks like this, right? You've got R1 here, you've got R2 here, but this node doesn't really act like a node because this capacitor cannot transmit current. It cannot have current going through it while it is attached to a voltage source. So let's write that out deliberately. It cannot have current through it while I missed a letter there. While connected to a voltage source. It actually can't have current through it ever, but it can produce a current. But we will get there as well, right? So second situation. Second situation is t equals n greater than 0. So we are at some time in after the switch closed. And at this time, the switch opens back up again. So now this circuit no longer exists, right? We only have this. So the mesh with the source on it is now no longer connected. So the only circuit is between R2, and the capacitor. Right? And if you apply our analysis methods, if you try to analyze this circuit this circuit at this point, all we can really do is look at this section. All we can look at is R2 and the capacitor. The capacitor is now draining. It now drains. And only R2 is powered. In this case, the capacitor is acting like a source. It's not a source, okay? I know that that's going to be a weird distinction, but these are not the same type of devices. This one can generate, right? Generates voltage. This one stores voltage generated elsewhere. So, if you started with this, nothing's going to happen. This capacitor cannot do anything with this resistor. If you had a capacitor and a light bulb, this light bulb is dead. This circuit is inert. It doesn't do anything because this capacitor has not been filled yet. However, since this capacitor was filled, since we spent enough time with the switch down and the voltage source powering this circuit, this capacitor filled up. And since it's full, since it has a high potential difference, it can now provide power. Capacitors only provide power when they have previously been connected to a voltage source. They are not currently connected to a source and are currently connected to a resistive device. Right? So we need the impedance, right? We need the R part of V equals IR. We have the V. If we have the R, then we get current, right? Because that's kind of the magic of Ohm's law, is if you've got two of them, you have the third one. You have spawned the third one into existence. Which can be abused sometimes. It's fun. So, that's kind of the magic of resistors. So, over time, because I seem to have misplaced a page, so over time, if we look at the third situation, the 3 where time is t, which is very, very much larger than n, the switch is still open. So when that occurs, when time just keeps on rolling into the future, this capacitor is eventually going to drain out. And it's gonna drain out very, very similarly to a bathtub. You know that a bathtub is an exponential decay function. Exponential decay function. And if that doesn't ring a bell, don't worry about it. Exponential decay just means that it uses the exponential function, e, with a negative value. It's literally of form this. There's a constant. There's some constant up here times the exponential function e to t over Greek t. And we're not gonna think about this any further this week. But bathtubs and capacitors drain using the same math, a very, very similar graph. A graph that looks like that. So, over time, with enough time, the bathtub empties completely, and it's dry. Same thing with a capacitor. Over that is an unfriendly color combination. Over enough time, the capacitor can no longer produce the voltage that it has stored. It does not create the voltage. It cannot cause a current across whatever next resistor is in line with it. This potential difference is no longer is too small, because this potential difference decreases over time. So those are kind of the gist of capacitors, and we will get into the math next week, and some of this will connect. But for now, take a load off. We're gonna look at inductors, and frankly, inductors are a little trickier than capacitors because they use magnetism as opposed to voltage. So let's see how they behave. And before we go too far forwards, we are looking at DC sources only right now. So later on, we will look at alternating sources and see how this changes. But for now, I want you to think about this as we have only got a direct source. We don't have to think too much about the squiggly bits. So inductors. Inductors are squiggly bits, unfortunately. So they store power as a magnetic field. And they are controlled by the current going into the device. So if you have this attached to a circuit and you've got some current coming in, that is the thing that influences what this device is doing. So what is this device? This device is the inductor. So this we call a core. It's a hunk of metal. And this we call the coil. It's a coil of wire. So, of wire. We also call this a solenoid. And solenoids exist in a lot of machines. So, if you have a switch, which I don't know if you've ever seen this kind of switch for heavy machinery or entertainment machinery, they have this funny little magnetic wire, and they've got a little post up here, and they've got a coil of stuff on the inside. That's a solenoid. It is a solenoid switch. And these things are used to control when machines start and stop. Because when it's active, this switch comes down and it connects, and then the machine goes. And when it stops, very, very fast, at a very quick relationship, the switch can be turned off or reversed. The magnetism can be reversed, and the switch can be flung off of it. So this can cut the power to machines and makes manufacturing and, like I said, entertainment. So like a lot of the set drops and the lighting and rigging automation that happens in like circ performances are done with solenoid switches. My chance to nerd out a little bit. So solenoids exist in a lot of machinery. And what they are, like inductors, are electromagnets. And you may or may not be familiar with the idea of electromagnets. So we've got the words electro and the word magnet slammed together. So they are magnets that only exist while there is electricity going to them. So, you see, moving charges, so a current, right? Because when charges move, that's current. So, current induces a magnetic a magnetic field around the wire. So this is just a piece of wire. It has a current going through it. Well, because it has a current going through it, it's also got a magnetic field going around it. As that charge moves, it brings a field into existence around it. Well, now imagine what happens when you do that through coils of wire. Why, you've got overlapping magnetic fields. Hold on to that idea. We're going to get there. So, if you put a voltage on this nail, this is the nail, a very crudely drawn nail, it becomes magnetic. And I've included some YouTube links in your checklist for this week. So go check those out if you haven't already, to kind of get a visual understanding of what's going on here. So this nail can now pick up paper clips. That's not a paper clip. That's probably still not a paperclip. I digress. This nail can now pick up paper clips. It is producing enough magnetism. It is been magnetized, okay? Well, the coil induces a magnetic field in the nail, which is a form of energy. So this thing has a field. Its little charges on the inside have all been lined up. Its molecules have been lined up with charge, where they've got the positive charges on one side and the negative charges on the other. Well, hold on. That's the negative side of the battery. That's the positive side of the battery. There's a connection here, right? So this magnetic field, which in a bar magnet it looks like this. It looks like this. There's a field that kind of suspiciously almost looks like it's making its own circuit, right? That is able to magnetize other ferromagnetic, so iron materials. Iron is magnetizable, so iron-containing materials. You're not going to be able to pick up aluminum paper clips, but also aluminum paper clips kind of suck. They don't bend. But focusing. Inductors do the same thing, okay? Their goal is not to pick up paper clips, though. Their goal is to store this energy as magnetism in the core. And that's such a statement, and I'm so sorry, but that is unfortunately it. So how do we describe the ability to have to induce magnetic field within the core to store as energy? How do we describe that? We describe that with the word inductance. Let's make it a different color so it doesn't crash into that diagram. Inductance. And we represent that with the letter L. Right? Because I has been used. So we represent it with the letter L. L. And we describe it with the unit Henrys. After, yes, some guy named Henry. Represented with the letter H. So, inductance is a property that is derived from the material. And dimensions of the core. That kind of feels similar to capacitance, right? Where it's the material and dimensions of the dielectric. Well, here it's the material and dimensions of the core. But there's one more thing, okay? And the number the number of turns of wire around the core. So let's look at that. So this is the core, right? This is the core. I'm gonna erase those. So this is the wire. And these are the turns. So 1 complete turn, 2 complete turns, 3 complete turns, 4 complete turns, 5, 6, 7. 7 turns. You're not going to have to count that. If you have to deal with this, you're going to be told there's like 200 turns. Or N is 200 or something like that, and you're not going to have to count it because honestly, like, 10 turns for a nail electromagnet to pick up something small is great. Does not produce the kind of magnetic field storage power that would be usable in the real world. Great experiment if you want to go pick up some scrap stuff from Home Depot and play with magnetizing stuff and have to order new credit cards. Great fun. So I'm gonna give you the equation for this. Again, probably not gonna force you to calculate this or memorize this. This is just to illustrate where this value comes from, right? Where this comes from. And it comes from permittivity, rho, pi r squared n squared over L. Okay, so lots of letters. So this is also permittivity. But we're using mu instead. Your textbook probably still uses epsilon. I, however, wrote it as mu because that is the value that I am most familiar using. That is either one. It's permittivity. It's the same number as up here, right? Permittivity. It's the ease of electrons moving through the material. This is the area of a circle, right? Well, there you go. That's the area. Area of the flat face of the core. So if you have a rectangular core, then you're going to have length, width, core. N, well, that's the number of turns. And then L is the length here between the ends of the wire, right? So how much distance the coil takes up. So inductors are like top-loading washing machines, and let me explain that before you fall out of your seat. So washing machines need time to start or stop agitating. Stop agitating the clothes. All right, well, inductors agitate electrons. Right? So, or more, not electrons, but the magnetism. So, the inductor coil, it's agitating the magnetic field, right? Well, it takes time to do that. It can't immediately have a magnetic field. It takes time to spin up. This takes time to spin up, right? So, washing machine needs a source of water, right? To cause the cleaning. Right? So it pours water in, and that water has to come from somewhere, and that water comes from your pipes. It has a source. it has to have something fluid through it. Well, inductors need a source of current. To cause the magnetic field. Right? And both of them have a center post to help the process. Right? Both have a center post. It's just this one winds towels around it, and this one winds wire around it. So they're very similar in concept. Yeah, that sounds legit. And okay, I also recognize that there are washers that don't have center posts and aren't top loading, but we're gonna ignore that and keep with this. So again, without math, avoiding math for now, we're gonna look at the following situations. So at t equals 0, the switch closes. And it's gonna stay like this until we reach something called steady state. And then at t some value in greater than t, we are going to look at it. So a little weird, right? We got our timeline. We've got everything before 0. We've got everything up to t, which we're going to call steady state. And then we got everything after that, including and after that. So this was supposed to say comma t. All right, so situation 1. The switch closes and we get to steady state. I promise we're gonna explain what steady state means. It's not just a funky alliteration. So at t equals 0, the switch closes. The circuit is connected. So the switch is closed, but the inductor current does not change instantly. So what that means is that as soon, at t equals 0, as soon as the switch closes, there's not suddenly current flowing through here. Okay? As a matter of fact, current goes to the inductor, but the inductor is not operational yet. It takes time to spin up, right? Takes time to spin up. So, in fact, since L, the inductor, L, is not operational, it acts like an open circuit. An open circuit. So this is like this, which kind of means that R3 is disconnected, right? It cuts off R3 from the circuit. So if we were to apply our analysis methods, we'd have to ignore R3 because it no longer makes a circuit. So all we've got is this, right? So at the beginning, when an inductor first starts operation, it doesn't operate, right? It doesn't pass current. It acts like it's a break in the wire. So, second situation, when we get t is greater than or equal to steady state, right? Which I wrote in a incredibly obtuse way above, but what I meant was t is reaching steady state. Well, let's figure out what steady state is first. So So steady state is a condition. It is a condition of certain devices, and by that I mean inductors and capacitors, where it behaves nominally. Okay? And it generally occurs after a calculable amount of time in a given circuit orientation. All right, let's break that down, because hoo boy, that was a whole lot of words. So, it is a condition. It is a state of being, right? It is a state of being where inductors and capacitors behave nominally. So the word nominal, and to be behaving nominally, is normal. I know that nominal can sound like this is the peak performance. It is not. It is normal. So until steady state, these devices don't operate the way we expect them to. Just something to keep in mind. So, generally occurs after a calculable amount of time in a given circuit orientation. So, calculable means that there's a formula for it, right? There's a formula. You can calculate it. There's a formula to find how much time it takes to reach steady state. Again, not doing the math today, so we are not gonna get into what that formula is, but be prepared. There's a formula. All right? In a given circuit orientation. So, given circuit orientation. So, what that means is when the switch closes, right? When a switch closes is one circuit orientation. So, having the switch open, a circuit orientation. Switch closed, different circuit orientation. These two are different. Different circuit orientations. Okay? So, just means that, hey, it's been switches closed for a long time, right? It's been switches open for a long time. So, both capacitors and inductors have steady states. But they have them, but they're slightly different. And first of all, before going too far further, this steady state just means that its voltage and current behave in a steady way, right? They've reached a level where they are even. They are not changing drastically anymore. We look at what we call IV characteristics of devices, where you map current and voltage, and you look at this graph that looks pretty recognizable to anything else that has a steady state or has a window of reliability. Looking at materials students, I know that you guys recognize the elastic plastic graph. Yeah, it's kind of similar. So, essentially, when you get to this point, there's no great change. There's an asymptote here. This is steady state. Up until here, who knows? There be dragons there. That's dangerous stuff. But here, forwards, you can use it. You can use the device. But we're not gonna dive too deep into that. Just understand that pre-steady state there be dragons. At steady state and further, yeah, you're good. You're safe. You can calculate that. You can graph that. You can understand that. You can predict how it's going to behave. Pre-steady state, there be dragons. So, back to what these steady states act like. So, a capacitor, right? Capacitors that have been connected to a voltage source for a long time are in steady state. And I say long time because that's the wording that comes up in problems. Something that has been connected for a long time might as well have been connected for infinity time, right? So it's had all the time in the world to get to steady state. That's what long time means. And inductors that have a current across them, right? So inductor, current, and then, this one's grounded on one side and it's got a voltage on the other, right? So there's charges accumulating. Well, this one has a current going over it, or, to it, for a long time, are in a steady state. That's kind of the important part here is time. We've given it enough time that time is no longer really a concern, except when it's draining. We'll see that next week when we get to the math of these things. So, back to the circuit. This circuit, right? This circuit that up until steady state, but not at steady state, is behaving like an open circuit. Well, now we're looking at when it reaches steady state, and all the time after that. Well, at steady state, the device's behavior stabilizes. Right? So we've got that we're charting I on one side and V on the other, and we've got this kind of suspiciously exponential looking graph where at some point things just level off, and it's nice, and it's steady. Yeah. It stabilizes. This is steady state. And if nothing changes in the circuit, if this doesn't suddenly die, or we don't switch this out, we don't for some reason hot swap a resistor and change the currents off of this, it's gonna be steady forever. So now the inductor behaves like a short circuit. Yeah. Okay. Cool. I don't know why I left that or there. What? Wasn't this device supposed to do something? Alright, so short circuit. It's a short circuit. It is connecting these 2 points now directly. A short circuit is a wire that does not contain a device. It's like a blank wire. Or what we've been calling blank wire, right? So, let's think about it this way. If we draw a short circuit here, if we put a blank wire here, well, this resistor's not going to get any love. because this wire has a lot less resistance, since it's ideal. Since it's ideal, it has 0 resistance. So all the current's gonna blast down this before it even bifurcates to this resistor. Well, I don't know about you, but that looks like a much shorter circuit than it was before. It is a much shorter length of wire to be going through, right? So that's kind of how I imagine the phrase short circuit came to be is, well, we've shortened the distance between these 2 points by making them effectively the same. They're effectively the same point, right? If you short these 2 points, you're bringing the wire together like this, and it no longer connects to the rest of it. Yeah. Cool. Very short circuit. Alright, so short circuit in this case is not a bad thing, okay? All it does is connects this R3 resistor to the R2 resistor and the R1 resistor very directly. Nothing else connected. In this case, short circuit bad, because now you're shorting out your power source, and this thing's gonna start sparking, or smoking, or catching fire. This thing's gonna burn itself out because it is shorted now. Not fun. In this case, the short circuit's fine because it's shorting a point to another device. It's shorting these 2 devices to these 2 devices, so actually this just becomes a node, right? This just becomes one very long node. This one, problematic to be short. So generally when we say a short circuit, in the real world, we're talking about this and it's bad. Technically, anywhere I've said blank wire, we could have said short circuit, but short circuit has its own connotations because of the real world. So I have chosen not to say that word until we had to explain why and when it happens. So in very complicated circuits, doing the DC analysis, so this is called DC analysis, which is to say, if everything was DC in this circuit, what would happen? The combination of inductors and capacitors may simplify things, because we know that this one's an open circuit, and this one, after a long time, is a short circuit, and it might bypass some devices. It might cut off some devices. And then you don't have to analyze them because they're not attached to the source in DC. So, again, important, these behaviors we covered are for DC only. These devices, the behaviors, they will behave differently under AC, okay? And we'll get there in like week 14-ish, because we also need to be able to do AC analysis. But just like doing math with resistors was easier to learn the principles on, doing math with DC, that simplification of AC, that point in time, is so much easier to learn this stuff on DC and then practice it a little bit on AC than it is to throw everything at you all at once and hope something sticks. So, that's going to be it for today. Next week, we are going to look at RC and RL circuits. So these are resistor capacitor and resistor inductor. Because inductor starts with the letter L. Yeah, totally. There's way too many things named I, honestly. I and V are letters that we are sorely out of in electronics. But anyway, these are specific circuits. They take a little bit of work. There's a lot of math to them, but we've simplified them down as much as we can. So don't worry too much. We'll get there. We'll get you through it. Yeah, so that's it. Good job. Go let this percolate. Go read a book, play video games, eat some food, hang out with friends, do something to relax, and have a good week. Bye-bye!